That day at Daria seems to be fine until...
Maybe it's a good day to tell boss about the new optical biosensor to detect E. coli that we desperately need.
Did someone mention boss?
Boss, I would like to suggest you the latest biosensor for E. coli detection.
What's wrong with the biosensor that we are using now?
Boss, our current method for E. coli detection is conventional culture primarily based technique. So time consuming. We have to carry out the molecular proliferation step and incubation can take up to 24 hours. Methods like multiple tube fermentation, plate count enumeration, and membrane filter usage are such a hassle. Other than that, PCR with nucleic acid-based strategy appears to have numerous obstacles as it detects each visible and dead cell and could be very complex with complicated standardized protocol. It also has low sensitivity. The application of reverse transcript tests have solved the hassle and has become extremely handy in distinguishing between viable and dead cell, but includes an exceedingly poisonous compound, such as propidium monoxide, for discriminating between live and dead cell. Its downside had high toxicity and expensive. And lastly, immunotherapy method that use laser only give result within 24 hours, working better than traditional method but require significant time, skilled operators, and expensive equipment.
Well, I believe our methods for E. coli detection is still relevant. We don't have to fund for a new biosensor protocol.
And I believe that quantification detection of E. coli is critical step, not only in our milk factory, but also environment, medicine, and pharmacy. Boss, we need to upgrade our biosensor to a selective, rapid, and accurate procedures for identifying the microorganisms.
I mean, chill, we have never received any poisoning complaint or anything regarding our products.
Not just common food poisoning, boss. Most E. coli produce type 2 Shiga toxin. This toxin can result stomach pain, diarrhea, inflammation, secretion of intestinal fluid, ulcer, even extreme instances like hemorrhage, enteritis, and hemolysis, which is found mainly in babies and younger children. I have read about a new biosensor which incorporates nanotechnology. We no longer need sophisticated instruments to identify E. coli. Okay. Boss, caught red. We have received our very first case of contamination. The lab test show it is E. coli. The customer is demanding a compensation from us.
What a timing! Call for some suppliers for the latest optical biosensor, please. A few days later, at Daria's meeting room.
Good morning and a very good day to all of you. Thank you for having us today and for choosing our optical biosensor technology for your food safety procedures. In total, there are 7 optical biosensor technology that are available in the market, which are fluorescent colorimetric, surface enhanced Raman spectroscopy, surface plasmon resonance, chemiluminescence, paper-based and smartphone-based optical biosensor. Today, we will introduce the first 5 and let's go through each of them. The very optical biosensor uses fluorescent technology. It is further divided into 2 categories, label-free and label-fluorescent biosensor. In a label-free fluorescent biosensor, polymycin B (PMB) is fed with up conversation nanoparticle UCNP. Polymycin B specifically binds with lipopolysaccharide of E. coli, forming a bacteria PMB UCNP complex. The complex was resuspended in PBS to measure the fluorescence at 801 nanometer under 980 nanometer light excitation. The fluorescence intensity increases as the concentration of E. coli increases. This method removes experimental uncertainties due to the effect of biomarkers on molecular conformation. By the obstacle of active binding epitopes, steroid hydrins, or by the inaccessibility of a suitable marker that work equally for all molecules in an enzyme. In a second fluorescence biosensor, which is a label fluorescent, it is further divided into 3 categories based on its biosensing elements. There are antibody-based, epitomal-based, and DNA enzyme. Base biosensor. In antibody-based label fluorescence biosensor, protein gene-modified MNP were injected and captured into the channel due to the presence of the multi-ring high-gradient magnetic fields. Next, monoclonal antibody against E. coli were injected, and the immune magnetic nanoparticles were formed through specific binding of the protein G to the Fc fragment of the antibodies. Then, bacterial sample was injected into the channels, and target bacteria were captured by the immune MNP, forming MNP-MAB bacteria complexes. After that, quantum dots, which were modified with the biotinylated anti-E. coli polyclonal antibodies, were injected into the channels to react with the magnetic bacteria, forming MNP-MAB bacteria PABQDS complexes, which is fluorescence bacteria. To determine the concentration of fluorescent bacteria, the fluorescent bacteria were flushed out of the channel in the absence of multi-ring HGMF. And the intensity of the fluorescent bacteria was measured with a handheld optical detector. Label fluorescence detection approaches are sensitive and convenient method used to detect and diagnose viral field. Also, this method proposes numerous advantages such as being easily manipulated, high sensitivity and selectivity, one-step detection, and appropriate durability.
The second optical biosensor in the list is colorimetric biosensor. There are two types, which are antibody-based and aptamer-based biosensor. In aptamer-based biosensor, GNPs were modified with mercaptophenylboronic acid and then firmly adsorbed on the surface of E. coli 0157H7 through electrostatic adsorption and boronate diol interaction. GNPs can catalyze the oxidation of the peroxidase substrate TMB by H2O2, producing a typical blue color for TMB within 10 minutes, resulting in the solution exhibiting maximum absorbance at 652 nanometer. Peak intensity at 652 nanometer becomes stronger when E. coli 0157H7 concentration increase. Colorimetric nanobiosensors are very favored for their simplicity, low cost, and no need for complex types of equipment for result readouts. These biosensors have advantages such as cost effectiveness, quick and easy response, no need for an operator, and complex equipment, but due to low sensitivity, have limitations. The third optical biosensor is surface-enhanced Raman spectroscopy. It is a super-sensitive and non-destructive technique that is becoming one of the most promising approaches to biological analysis. This method makes it possible to detect low concentrations of adsorbed molecules on the surface of plasmonic substrates.
The fourth optical biosensor is surface plasmon resonance. Firstly, lectins were immobilized on the CM5 chip through a self-assembly monolayer SAM to capture E. coli 015H7. The accumulation of E. coli bound to the surface resulted in an increase in refractive index, which served as a SPR signal. SPR response increased with the increasing concentration of E. coli, where the more cells bound on the chip surface, the higher the SPR response of the lectin-based SPR biosensor. SPR detection is now being applied to detect cancer markers, antibodies, drugs, and hormones, among other biomarkers. Plasmonic nanostructure with a higher refractive index sensitivity or nanostructure with a limited depth of field closer to the surface lead to significant SPR changes for a given detection event. The last biosensor that we have installed is chemiluminescence biosensor. First, the captured antibody is immobilized on the surface of magnetic beads. Samples infected with E. coli are then added to induce primary immunorecognition, followed by a biotin conjugated detection antibody to initiate the second immunorecognition event. Avidin conjugated glucose oxidase is attached to the surface of magnetic beads through a biotin avidin recognition reaction to form immunocomplex magnetic beads. Next, unbound glucose oxidase antibody is washed out with a buffer solution after the immunological reaction. When the immunocomplex magnetic beads are exposed to a solution containing glucose, glucose oxidase catalyzes the conversion of glucose into gluconic acid and hydrogen peroxide. Finally, lactase and luminol are added to produce chemiluminescence signals, and the E. coli is quantified through a chemiluminescence assay of the solution. Luminescence has many advantages, including good sensitivity and rapid detection, extended dynamic range, relatively simple equipment, and low cost due to a lack of need for an external or optical light source. That's all for the mechanism and benefits for each biosensor. Do you have any inquiries?
Yes, what would you recommend for our company, please?
These new optical methods have been used to complement or replace traditional methods for E. coli detection as it gives high-speed outcome and sensitivity. We know that food factories need a biosensor with a low detection limit to ensure their food safety. The optical biosensor with the lowest detection limit is the enzymes-based label fluorescent biosensor as low as 1 CFU per milliliter, followed by aptamer-based label colorimetric biosensor at 7 CFU per milliliter. Both antibody-based colorimetric biosensor and surface-enhanced Raman spectroscopy come at the third with 10 CFU per milliliter detection limit.
Okay, I believe the colorimetric biosensor will suit our fund. May you elaborate more on the efficacy?
Yes, currently we are facing some challenges. For colorimetric biosensor, its paint color changes on the test strip can be nearly indistinguishable from the background substrate, which can result in miscategorized sample detection. Hence, we are measuring the colorimetric signal produced by the biospecific accumulation of colorimetric probes and recording the results to get accurate readings. Besides that, for surface plasmon resonance biosensor, plasmonic nanostructures with a higher refractive index sensitivity or nanostructures with a limited depth of field closer to the surface lead to significant SPR changes for a given detection event. To improve this, two-dimensional materials has the possibility of enhancing the sensitivity of SPR sensors because it has extraordinary photoelectric properties, unique layered structure, and high surface to volume ratio that can enhance the absorption of biomolecules. Lastly, using silver nanoparticles in surface-enhanced Raman spectroscopy can overcome the low sensitivity problems inherent in Raman spectroscopy.
Great. We will agree on the colorimetric biosensor and make sure to update us on the latest devices improvement. Nice working with you.
Thanks for watching, and this is a video by Group 17.